lectures all the way from China live, and hopefully everything will go smoothly. Hongjun Xiang has obtained his bachelor's degree and PhD in China from the University of Science and Technology. And then he went to North Carolina State and NREL as a postdoc from 2006 to 2009, and joined the Faculty of Physics in Fudan University as a full professor in 2010. He was awarded the International Center for Theoretical Physics ICTP Award in 2018, and he's a fellow of the American Physical Society. I'm going to let him speak for himself, but just to point out the kind of exciting things that Dr. Xiang, Professor Xiang has been working on is, for example, electric field switching of magnetic systems and multi-ferroelectrics. And I think it's really exciting. He showed in detail the particular way that this happens in terms of the spin density and its interaction with ferroelectricity. So these pictures here show the spin density and for up and down state, and you can see that the spin density is different. So it's a way to control magnetism through electric fields. But I think at this point, we will go directly to him and hear what he has to tell us today. Okay, it's all yours, Hongjun. Afterwards, there will be a question and answer session, and you can type your questions in anytime, even during the talk, but we'll address them after the talk. So just use the Q&A button on your app. Okay, with that, we'll turn it over to Hongjun.
Okay, so can you see my screen?
Yes, just make it full screen. Yeah, there you go.
Okay. Thank you, Ronald, for the introduction, and also thank you for giving me this chance to introduce our recent work on our work. So today I will talk about our recent package we call the PASP, Property Analysis and the Simulation Package. So let's change to the point. Yeah, and the simulation package for materials and its applications to ferroelectrics. I'm from Fudan University. Okay. Here's the outline of my talk. First, I will give a brief introduction and also the motivation of this work. And then I will introduce our package, its underlying series and the methods. And I will show some example applications of PASP to ferroelectrics. And if I have time, I will discuss our recent work on ferroelectricity without breaking in motion symmetry. And finally, I will give a brief summary. Okay, so we all know our human being undergoes different kind of ages, from Stone Age, Bronze Age, and Iron Age, and now Silicon Age. So what is the next age? So I think maybe a quantum material age will be in this age. So what is a quantum material? Quantum material means it may display some quantum effects. This kind of material it will have rich physics because it has a molecular degree of freedom as a spin, a charge after a lattice, and also a topological degree of freedom. And also this degree of freedom are interactive with each other. And they have rich physics and have also have many emergent phenomena. For example, it could have a motor insulate and also topological insulate and also magnetoelectrics, including modifiers and also for quantum computing. And the quantum material can have many applications. For example, in the field of information technology, it can be used to make ultra low energy consuming and high speed and high capacity and high security device. Among quantum materials, all research mainly focus on ferromagnets and ferroelectrics and also modifiers. So I think all is we all know very well what is ferroelectrics and also ferromagnets. And if a system has both ferromagnetism and also ferroelectricity, and we call this system displays multiferricity. And the concept of this multiferricity is extended to all the system well. So if the system has a magnetism and also ferroelectricity, we also call this system as a multiferric system. So density function theory is now widely adopted for simulating materials, including quantum materials. This table shows the density function theory is actually very useful. This table it shows the highly sized tables of our physical view. Actually we can see all the 10 most cited papers in physical view, and we found 1, 2, 3, 4, 5, 6 papers are related to density function theory. So this we can see density function theory is very useful for studying materials, including quantum materials. However, the traditional density function theory has some shortcomings. For example, it is computationally demanding. This is because usually the computational time is proportional to the cubic of the number of atoms in the of the system. This we call the n-third square, n-third scaling. And another shortcoming of density function theory is that it can give you the whole number. I mean the final results, but it may not give you the fixed picture without further analysis. For example, it can give you a total polarization using the Bayes calculation, but it is hard to understand how the polarization the mechanism of the microscopic mechanism of this polarization. So to solve the problem of the density function theory, we developed a package called property analysis and the simulation package for materials. In our materials, it can deal with different kind of properties. The central part of our material of our package is the symmetry analysis, the group theory analysis. For example, based on this symmetry analysis, we can use the unified model for type 2 modifiers. I will discuss this later. And also, we can also do structure prediction, especially the structure prediction for quantum material. For example, we can predict the distortion of Pascal structures, including rotational rotation and also ferroelectric distortions. And we have a different kind of optimization techniques. For magnetic system, we can also compute the spin wave dispersions and another important part in our package is the effective Hamiltonian measures. We include the Tat binding model for electronic degree of freedom, and also the atomistic Hamiltonian for atomic displacement and also spin and degree of freedom. Within our package, include two kinds of potentials forms. One is we use the polynomial Taylor expansion form, and another we can use the machine learning neural network form. After we construct the atomistic Hamiltonian, we can perform monocolor simulation and also molecular dynamics to obtain the thermodynamic and also kinetic property of the system. An interesting import feature of our code is that we can treat multiple degree of freedom simultaneously. For example, if the system has a spin charge and after that is allied degree of freedom, we may treat this degree of freedom in a unified framework. Okay, let's discuss the unified model for type 2 modifiers. So previously we introduced the concept of modifiers. Actually, modifiers can be classified into two types. So in type 2, type 1 modifiers, the ferroelectricity and magnetism have different origins. For example, bismuth ferrite oxide. So the ferroelectricity is due to the long pair of bismuth, but the magnetism is due to the iron 3+ iron ion. However, for type 2 modifiers, the ferroelectricity is directly caused by the magnetism. So this magnetic order breaks the inversion symmetry. So this is easily to understand from the symmetry argument, but the macroscopic mechanism of this magnetic order induced ferroelectricity is not easily understand. So therefore, we proposed the unified model for type 2 modifiers in recent years. So basically, for example, for this demo, we can write the polarization induced by the spin order into this form. This the first form, the first term we call the single side term. This the R means two of the individual sets, and this is a single set, and this is the interset. So we have an index of R and J. So they're different set. And this we have this different kind of coefficients, and for this coefficient we can we propose the fourth state method to compute this coefficients, and then we can use this to calculate the polarization for given spin order. So, and we can also decompose this different kind of contributions into pure electronic and also anodic displacement or and another lattice deformation contributions. I will also discuss briefly our genetic algorithm for predicting ground state of magnet. So in the field of structure prediction, genetic algorithm is widely used. The conventional genetic algorithm actually is very simple. For example, we have two different structures, this one and this one. So so we can cut each structure into two parts, into two halves. So this and this, and then we combine these two halves into a new structure. and we call this operation as crossover, and then we obtain a new child structure, and we can do structure optimization to see whether this gives a no energy structure, and then we will iterate this process and to try to find the lowest energy structure. And if we consider a magnetic system, so in this case, we need to consider the spin degree of freedom. So actually, it's very easy to consider spin degree of freedom in genetic algorithm. So this is just we can just keep the spin direction on the atoms, and when do crossover operations, and we just keep the spin directions. Then actually, it's very easy to adapt this genetic algorithm to predict the ground state structure of magnets. Okay, then I will also discuss our effective Hamiltonian method in PASP. So effective Hamiltonian method actually is not widely used in the field of magnetism and also ferroelectrics. But usually people only treat all kinds of degree of freedom each time, and they usually consider simple interactions. For example, for a magnetic system, usually they employ the Habsburg model, and for this is just the dot product terms, and for the alloy, people usually use the Closely branching Hamiltonian, and for the ferroelectrics, this Hamiltonian actually is developed by Vanderbilt and his collaborators. Usually, for the short range interaction, they consider the second order pair interactions. In our package, we try to generalize this effective Hamiltonian method. So we are trying to treat multiple degree of freedom. For example, the system might have a spin degree of freedom and atomic displacement atomic displacement degree of freedom, and also may have alloy degree of freedom. And this kind of interaction between this degree of freedom could be complicated. So we are trying to encode all kinds of complicated interactions. So we use the group theory to find out what kind of interaction will be present in a system with a multiple degree of freedom. So we have find the invariance of these different terms. To see this in a more clear way, we will give an example. So for example, if we consider this cubic strong magnet system, and we consider this two magnets and two magnet set, and this magnet 1, magnet 2, and we consider the spin and also atomic displacement degree of freedom. So from our group theory analysis, we find that actually there are terms like this. So this is S1x, S2y, U1x minus S1y, S2x, U2x. So U1x and the U2x, it means the displacement of the magnet atom. So we can say that if there is no atomic displacement, so U1x and U2x equal 0. So this term will be 0. Actually, one can say that this is S1x, S2y minus S1y, S2g. So actually, this is the one component of the geometric Marie interaction is the DJ term. So when there is no atomic displacement, there is no geometric Marie interaction. This is actually this is well known because there is an inversion symmetry in this architecture. However, when there is atomic displacement, so if this iron displaced along this x direction, so this is along x is this direction, and this also displays along this x direction. So this kind of displacement will break the inverse symmetry, and then it will give us to the Yamasaki Marin interaction. So this kind of term is actually the basic meaning of this term is the harmonic displacement induced the Yamasaki Marin interaction. So we can use the group theory to obtain all kinds of complicated invariant terms. But we found that there may exist too many symmetrical load terms in the effective Hamiltonian. For example, in a system with the spin degree of freedom and the atomic displacement degree of freedom, so the number of terms could reach 5,000. So this is the if we have 5,000 terms, then we have 5,000 parameters. So this is very hard to determine. But actually, we found that usually to describe a system accurately, actually not all interaction are important. Maybe only a small portion of interaction are important. For example, the important interactions are much smaller than n. So important interactions might be only in the order of 100. So the problem it becomes how to select the important interaction from all these interaction terms. So this is not easy to just to use this usual linear least square fitting method to get this so solve this problem. This is because if we use the simple linear least square fitting method, we need to at least the data size, I mean the number of configurations obtained from the different calculations should be larger than the number of the possible interactions. And this is time consuming. For example, if you want to do 5,000 different calculations, then it's very time consuming, right? And then there is also another problem. So if we have so many parameters, so it may be prone to overfitting. So actually, as we have too many, the model is too complicated. So the overfitting will most likely occur. So we propose another method for to select the important parameters from the important interactions from all the possible interactions. So we first introduced a new realization terms to select a physical model. So the relaxation term is to use to minimize the number of terms. So this is the usual relaxation terms. So the lambda p terms. So the p it means the number of interactions in this model, and this is the sigma square. It means the variance of the fitting. So we are trying to fit to minimize these terms. So a good model will minimize the difference between the DFT and also the model, and also in the same time it will minimize the number of the parameters. However, we found that this widely used regularization terms is not not very used. It's hard to use because we found that for different kind of systems, the lambda parameter is harder to choose. But we found if we use a new realization terms like this, sigma square multiply this explanation terms, we found that the lambda parameter is around 1.0 to 1.1. So this is easy to choose the lambda parameters. Okay, we have another feature of our method is usually there are some method proposed before for the variable selection. So they usually just adding terms one by one. So each time they add one important terms, and then next they add the important terms from the remaining terms. But we find that that kind of process may add wrong terms. So actually, besides adding terms, we also deleting or substituting substitute terms. This we can remove the unimportant terms from the already selected terms. In this way, we think we can solve the variable selection problem. Okay, this is basically the some typical method we used in PASP. And then I will, in the remaining time, I will discuss the applications to ferroelectrics using PASP. First, I will discuss the same frame case. We have the intrinsic origin of the enhanced ferroelectricity in same frames, and I will also introduce we used to work on a hybrid perovskite. We found actually a large non-polar molecule could induce the ferroelectricity, and I will discuss all results on the electrophilic switch of topological mechanism in two-dimensional modifiers. Okay. This is the okay. We all know in this A set that this for example in bismuth ferrite oxide, the ferroelectricity is due to the A set long pair iron, the bismuth, and also in the literature, people found that the A set polar molecular can also give rise to the ferroelectricity. We are trying to answer this question. So can a hybrid perovskite with a long polar molecular be ferroelectric? So we found that actually this so people usually consider the long pair iron as an A set will give rise to ferroelectricity, but we found that even when the long pair iron is located as the B set, this can also give rise to ferroelectricity. So this can be seen from this simple model. So we consider this simple model. This the metallic set, for example, is tin lead, and this is the iron. This for example the anion, and so we are trying to find whether the carton would like to stay in the center of this or between these two carton, this anion ligand, or if it will displaced a little bit from the center. So we can add consider the energy into two parts. So one part is we call the repulsion. So it means the repulsion between this and this, the co-electron of this and co-electron of this. So it's usually called the poly repulsion, and we simply just use the this kind of formula to simulate this effect. This is the LG potential, the repulsion part of the LG potential. And another effect is there are some bonding effect. So this this can, for example, the p orbital, the empty p orbital of this can interaction with the occupied p orbital of the atom. So this kind of interaction the energy can be written as these forms according to the perturbation theory. So this is a hopping. The hopping between these two, we can write this in this form. This depends on the distance between the cation and the ion, and we use this formula according to Harrison's tight binding method. So we found that if the distance between the center and the ion is small, then we find that the lone pair would like to stay in the center. So there's no ferroelectricity. However, if the distance is large, then we find that it will displace from the center symmetry position to the ferroelectric state. So in this case, we found that the second order geometric distortion effect is stronger than the Pauli repulsion. So this will give rise to the ferroelectricity. Then how to realize this kind of phenomena? So we found that we find this may occur in this kind of material. So we consider molecular. This NH34, and this is a long polymer molecular. And we put this molecular at the A site of the proscat, and then we found this for the three-dimensional system. So the B side is tin, and the X side is atom. And then we found that the ground state is the ferroelectric R3M-like structure. So it has it has this kind of polarization. However, at zero pressure, this structure is not the lowest energy structure. But we found that on the small pressure, for example, 4.5 gigapart, and then this kind of three-dimensional structure becomes the lowest enthalpy structure. And okay, I think I only have 10 minutes left, so maybe I skip this part and then I go to this part. Okay, so I will talk about electrophilic switching or topological magnetism in two-dimensional modifiers. Recently, scanning attracted numerous interest because it could be used to make a high density storage device. People are trying to manipulate this scamming defects. For example, some people are trying to use the magnetic field pulse to manipulate scamming, and some people can use the spin polarized current to manipulate scamming, and also some people propose that we can use the thermal excitation to manipulate scamming. However, the electric field will be an ideal way to manipulate scamming because if we only use the electric field, for example, voltage, then it have no geo heating, so it can save energy and it will be fast. So people are trying to use the electric field to manipulate scamming. However, the question is currently electric field has been used to write erase scamming, but can we switch the topological charge from the -1 to +1? That's the all question. So the topological charge is defined in this formula. So this is the magnetization and magnetization derivative of which rate to the x, which rate to y. This is the integral of this. But we know that the magnetism breaks the time reversal, but the electricity is only electric field only breaks the spatial inversion. So how can we control the topological charge using electric field? So this seems very difficult. But fortunately, we found that there may exist a known mechanism we call the EPDQ mechanism. We can manipulate the sign of the topological charge. This is so first we have an electric field. So the electric field can couple to the electrical polarization. We can control the electrical polarization, and this electrical polarization is connected to the sign of the Yamsitsky-Maria interaction strength. And then we found that this if we change the Yamsitsky-Maria interaction, and it may change the sign of the topological charge. But we found that actually there are some important fact related to the entropy. So I will explain this later. So this entropy is also important to for this to realize this kind of mechanism. We select the system is manganese oxide iron 2. So this is the periodical structure. It's a two-dimensional structure. So this is the top view. So we have this this vanadium, and this is oxygen. This is iodine, and we have this chains, vanadium oxygen chains along the A direction. And we found actually for in the ferroelectric state, this chain, okay, remember this you can see the direction of this kinetic system is different. So this is the A-axis. So we can see from the periodic state to the ferroelectric state, this vanadium where the displacement is placed from the center of this two oxygen. So this will give rise to the ferroelectricity. And then this also will give rise to the Yamsitsky-Maria interaction. So in this case, there is no Yamsitsky-Maria interaction, but in the ferroelectric state, we have this Yamsitsky-Maria interaction. And in the opposite ferroelectric state, the sign of the vector of the Yamsitsky-Maria interaction vector will be opposite to this case. So this can be deduced from the symmetry argument. And previously, actually, there are some study. For example, this work they predict the ferroelectricity and the ferromagnetism in this two-dimensional system. But from our derivative calculation, we combined with our first data method, we constructed the spin harmonious, and we found that actually the ferromagnetic state is not the ground state, and we found the ground state is the spiral-like state, like this. This ground state is this spiral-like, but we found actually there's metastable bimaran state, in this two-dimensional system. So so in this bimaran, actually we have this anti-vortex and vortex. So this is the direction, spin direction. So mostly the spin is in the plane, in the AB plane. So actually, when the spin is in the AB plane, the entropy is in plane entropy, in plane, easy plane. So in this case, the topological mechanism becomes a bimaran instead of scamming. So the most of spin is in the plane, but in this part, in this anti-vortex and vortex part, there are some outer plane component of the spin. So one is along C and another along minus C. So we use this kind of symbol to denote this kind of bimaran. So this is another state. So they just change the Z direction of this of the spin configuration. So this bimaran is topological. So actually, they have a non-zero topological charge. So this kind of, for example, this one is we call the A up or V down. This kind of the topological charge is -1. So this the topological charge contribution, they are the same, and the one each one contribute 1/2. So the sum of this is -1, and the other one is A down V up. This is the topological charge is a positive one. So we will show that on the electric field we can switch from this configuration to this configuration, and then we can realize the switching of the topological charge on the electric field. This is the Monte Carlo simulation to show the evidence of bimaran. So what will happen under the electric field? So on the electric field, we found that, for example, we start from this state, and this is A up, V down, and then when we apply the electric field, in this case, we found this is the periodic state. The periodic state, and we find the entropy change. So initially the spin is in the ABA in plane entropy, but in this periodic state, this entropy becomes auto plane. So in the periodic state, when there is no polarization, this will becomes the this domain. All the spin are along the C or minus C. So we found that actually we can switch this one, the spin direction along the Z axis will not change. Actually, on the electric field, it will change the anti-vortex to vortex, and from the vortex to anti-vortex. And in this, in the same time, the topological charge changed from -1 to +1. Okay, so this kind of mechanism, it needs the several effects. So first, we need to change the Maria interaction, and then the change on entropy is also important. So this will keep the spin direction along the Z-axis. Okay, maybe I will use 1 or 2 minutes to introduce our recent work. So usually people believe that periodic inversion symmetry is a prerequisite for ferroelectricity. For example, in this berry titanium oxide, in the periodic case, this is our inversion symmetry, but in the for the ferroelectric structure, it have no inversion symmetry. So we are trying to answer whether it is possible to have a ferroelectric-like state with inversion symmetry. So in this state has inversion symmetry, and this state also has inversion symmetry. So we consider a one-dimensional model for this unusual ferroelectricity. So in this 1D structure, so this is the charge order state system. This is the anion. This is the one anion set, and these two are cutting set, but they have different charge state. So it's +1, +m, and +n. So this we call this state 1. So we can see this kind of structure, they have inversion symmetry. So this is the inversion center, and this is the inversion center, right? And another state we call the state 2. So state 2, the difference between state 2 and state 1 is the switch the charge order set. So for example, this becomes a +n, and this becomes a +m. So they both state they have they have the inversion symmetry. We found that if we from this state 1 to state 2, this can be achieved by charge transfer. For example, we charge transfer this n -m electrons from this set to this set. We can we can obtain state 2 from state 1. So this kind of charge transfer will give rise to the polarization difference. So there will be is like this. So it will be non-zero. So this suggests that the polarization difference between the two central symmetrical charge order state could be non-zero. So this means that maybe a electric field can induce the transition between two symmetrical state, two central symmetrical state. So this is the one-dimensional model, and then we found that maybe this could occur in this charge order system, barrier bismuth oxide, and we suggest if you apply electric field along this direction, then the charge transfer will occur for both chains, and this is the transition state of this transition. So this is basically what we proposed in this our recent work. Okay, I used all my time. So basically, this is the simple summary of my talk. And this work is done in collaboration with Professor Xingao Gong in Fudan University, and also Professor Xiu Chen, and also my postdocs, and also my students from Fudan University. And also some of the work are done in collaboration with Dr. Fudan Song and Professor Lavender Balash from University of Arkansas. And thank you very much for your attention.
Okay, great. Thank you very much. And I think we have time for some questions now. So people can please type your questions into the Q&A box. And as they come in, I will read them. Let me start out. I have a couple questions. One is I was wondering if you could say something about the accuracy of DFT for computing these DM interactions. Does the antisymmetric exchange come out accurately compared with the experiment?
Oh, okay. Yeah, this is a good question. So how accurate can we calculate the spin interaction parameters? Yeah, I think this yeah. For example, in our density function theory calculations, we have some parameters. For example, the U value in the Hubbard plus Hubbard U calculations. Sometimes the U calculation, the U, if you change the U, it will change the Yamashevsky Marin interaction. I can only say that usually it's magnitude. The order of the magnitude of the Yamashevsky Marin interaction is in the similar order to the examined results. Yeah, but
okay. So it seems like it is something where you need to use the DFT plus U approach to get accurate numbers in general. So okay, that's a good thing to know. I still don't have, if anybody wants to type in a question, I would be glad to ask it. I can keep talking with Hongjun until we run out of time, but it's an opportunity for people to ask. So, there's like 40 of you out there, so maybe someone has some questions. A second question is I'm wondering if there's something like a relaxer for these multiferroics, or is it always going to be a very sharp hysteresis loop with the DM interaction?
Excuse me, can you repeat the question?
Is there something like, can we expect maybe some kind of relaxer-like system which has a more broad transition? Or is it always going to be a sharp hysteresis loop in systems that are driven by this DM coupling?
You mean DM coupling will change the relaxer?
No. I'm asking if there might be situations where you could have relaxer behavior in the multiferricity. If it's something you've thought about.
Yeah. This a good suggestion, but I have never thought about this possibility. Yeah, thank you.
Okay, and then the third question I have is just the accuracy of the effective Hamiltonian models. So after you go through this paring down of parameter space, like how many parameters do you end up with typically that are actually used, and how accurately do they fit the DFT plus U?
Okay. Yeah, this depends on the system. For example, if we only consider spin degree of freedom and we consider the spin Hamiltonians, then usually we need about tens of parameters. For example, 10, 20 parameters. And then we can usually the results agrees quite well with the DFT calculations. For example, the energy difference between the computed and between the model and the DFT calculations is about 0.1 MeV per atom. Yeah, something like that. But if you consider a more complicated system, for example, the Felix modifier system, for example, then we will have many parameters. In this case, I think usually need 100 parameters to get a reasonable Hamiltonian. Yeah, but yeah.
In the systems you showed, like the figures showing the different spirals and so forth. So are those ground states or are those excited states?
You mean this one?
No. Go back to your Marion's here. Like, are these ground states? These configurations?
In this, for this system, the ground state, magnetic ground state is this. Yeah, it is.
Okay.
Yeah, and this is not a ground state. It's metastable. It is stable. I mean, it is locally stable. Yeah. If you do local optimization, it will stay there. Yeah.
So at room temperature, do you expect these excitations to exist at room temperature?
At room temperature, okay. Let me see. Actually, we do monocolor simulations. So let's see with how the temperature.
Oh, I see.
Temperature there. Oh yeah. How? Yeah. No, in this case, the temperature scale is rather low.
I see.
So,
I see.
maybe at room temperature, yeah, it's just the periodical, paramagnetic system, paramagnetic state.
Okay, I have a question from Jen Musfeld. And she says, it seems like there might be two limits to the polarization without inversion symmetry problem. In the long time limit, the charge ordering that you predict might support an electric polarization, but a short time limit involving charge transfer excitation should exist as well. So she's asking if that's correct. Are there different limits in long time and short time?
Okay, let me.
You can read a question.
Yeah. I'll open this. So there are 2 minutes, 2 limits to the. Okay. Yeah, at a short time. I think ask me should be right. Yeah, at the dynamic limit, the electron will hop back or forth between these two different sets. This is a dynamic limit, and in the static limit, so the hopping between these two sets is I mean the time needed is rather long. And then this is a static limit. Yeah, I agree. Yeah, but this may depend on the specific material, I think. Thank you.
Yeah, thank you so much, Hongjun. We're out of time. Let me take over the sharing here, and thank you so much for that wonderful talk. And I actually learned a lot myself. So let me see if I can. Oh, I think you have to stop sharing. Yes, it was great. Thank you. Let me just put up my what happens to it. There we go.
Okay, thank you. Yeah.
Yes, thank you so much. It was great. And I want to mention the next talk and thank all of our participants. Oops, what happened here? There we go. So the next talk will be November 11th, and by Professor Gopalan from Penn State University, who will be talking about creation and dynamics of complex polar supertextures by design. So really looking forward to that. I'm not sure what we will do in December. We may have one. I have to decide on that. And January, we'll definitely take a break. And then we have the ferroelectrics workshop coming up in Ferro 2022. It'll be February 6th through 9th, 2022. We have an organizing committee now. The location will be probably in Washington, though there's still some slight chance of it being elsewhere in Maryland because details are not completely ironed out. It will be a hybrid meeting, and we will have both ability to join remotely and give a talk or watch remotely, as well as to come on site. If we have it at our my home laboratory, we have limited space, so we would have a limit of 60 people on site. So I think in the, it's hard to look ahead to February, but I think that that's reasonable for a hybrid meeting. If we have it elsewhere, we could have more people. So let me know if you have any feedback on that. It's a location and a limit. And please just email me if you want to talk about that. And the only thing is we will require everyone, if it's going to be at Carnegie and maybe I guess anywhere, everyone to be vaccinated and masked, and that's on site, and the speaker doesn't have to wear a mask during the talk. But other than that, and there's going to be some requirement of testing close to the meeting, either on Sunday before the meeting or or within 3 days of the meeting, rapid testing. So that's what we're coming up with there. So I want to thank everybody, and remember all of these lectures are available recorded online on YouTube, on the YouTube channel. And so refer you to the website for details on where that is, or the emails.